Hi, this is the second part of our exercise where we are using a support vector machine to read sentences in Cook Islands Māori and then determine the part of speech for each of the words in the sentence. So this is an example that you're going to find in your canvas. Example 1. It asks you to enter a sentence in Cook Islands Māori. Let's use the Kia orana, hello. And it correctly tags kia as a tense aspect marker and orana as a verb. Again, the word kia means may you be, shall you be, which is a time word. And then orana means healthy. So the whole sentence is may you be healthy, kia orana. And this is a simple classifier. Let's look at how it works. We have the code here, and we're using scikit-learn and pandas. The first thing we're going to do is read our input. Let me show you what it looks like. Here we have 4 columns, 3, 4, the previous token, the token itself, the following token or posterior token, and the part of speech of each token. So for the very first word in our corpus, it's the word kanga, which is preceded by the token ka, and the following word is tuatua. And the part of speech of kanga is a verb. So this is our very first example. For example, we have one here where the word is pau, the previous word is kia, and then there's no following word, so we just have the marker for no word. And then pau, our token, is a verb. And this toy input only has 2 types of parts of speech, verbs and nouns. And we have 1178 examples. I apologize. For verbs and nouns. So here we read our data set into the variable sim data. And the first thing we do is that we separate it into the features and the labels. So this instruction here tells you to drop the column token POS. And so X is just going to be the data, the features, So just the token, the previous word, and the following word. And then Y is going to be just the column token POS. So this is just the labels. Let's take a real quick look first at the Y. So as you can see, the first thing it did was to print all of the labels in the data set. The first one was a verb, then tense aspect markers, and the last one is a tense aspect marker. And then we have, the program itself. Let's print X for you to see what the features look like. This is what the matrix looks like. As you can see, it has names for each of the columns, and then the 0th element is this one here. Ka, kanga, tuatua. So these are the features, the token, the previous token, and the following token, which are stored in X. And then Y has just the labels. This is Y. All right. Let's comment those out for now. The next thing, and I want this for the example. There we go. I'm going to have this just to print the head of X, so the first 5 elements. And then I want to print also the labels for the first 5 elements. And this is just for us to see what's going on. as we see here, the 0th element is kanga, which is a verb. The word kanga is preceded by ka and followed by tuatua. The next thing we're going to do is to encode these words and transform them into numbers. So we're going to use the ordinal encoder to transform the values in X, ka, kanga, tuatua, kua, koputa, aya, into numbers. And then we're going to use, so we're going to create the object ordinal encoder, and then we're going to run X and transform it into an encoding. And this is going to be in the variable tx. Then we're going to use the label encoder to transform the labels in Y. So this is a sample of Y. We're going to transform those into the numbers that we're going to get in ty. So let me show you what those are going to look like side by side. Here I'm going to print the first 5 elements in the encoded features. And here I'm going to print the first 5 elements in the encoded labels. And by the way, I want this for later, not just yet. So again, I'm going to print the first 5 elements in the encoded features, and then the first 5 elements in the encoded labels. Let's see what happens. Here we have it. So we have that the 0th element is kanga, preceded by ka, followed by tuatua. This is a verb. The 0th element is its features are transformed into the numbers 21, 33, and 284. Again, this instruction on line 48 transforms the word ka into 21, the word kanga into 33, and the word tuatua into 284. And then it transforms the label V into a 1. And you can see that this is alphabetical. So TAM comes first alphabetically, so it's going to be the label 0. And V is the second one alphabetically, so it's going to be the label 1. And you can see it here. This one, the number 3, is a tense aspect marker, the word kua, and it is transformed into a 0 for the tense aspect marker. Tense aspect marker for sentence 3, a 0. And the null element is 0, the word kua is 58, and the word tati poki ia is 255. By the way, if you look at it very closely, you're going to see that the numbers are assigned by column. So this kua here, and by column I mean by feature. So this kua here is number 38, but this kua here is number 58. So if your words happen across features, they might not have the same number. These numbers are within each feature. All right, so again, we have read in our comma-separated value file, separated the features from the labels, then we encoded the features, and we encoded the labels, so that we now have numerical features and numerical labels. And by the way, I had this here. In case you ever want to know what a label is, there's an instruction called inverse transform, where you can send a numerical label, and then the encoder will inverse transform it, and return you the actual string label. I guess that string was not necessary there. Let's see. So as you can see here, I sent the encoded label 0, and I inverse transformed it, and what came out was TAM. Here, I sent the encoded label 1 and inversed transformed it, and what came out was V. The same 0 for TAM that we have here, and the same 1 for verbs that we have here. So this is what we have so far. Let's now create testing and training sets. I think this is from scikit-learn, right? Yes. It has very nice functions for creating training and testing sets. As you can see, we have the features for all of the data set, the labels for all of the data set, and then we specify the percentage that we want to assign to the testing set, 10%. And this is going to return 4 objects: the training features, the training labels, the testing features, and the testing labels. And by the way, this 10% selection is random. So every now and then you'll get, like, if you run the program twice, you're going to get slightly different results because the selection of the 10% is done in a random 10% of the sample. So here we have the training features and the training labels. Next, we're going to create a classifier. This support vector machine is going to use the radial basis kernel, radial basis function kernel, which is the one that expands blobs away from the center of our cluster. The default for the gamma value is 1 divided by the number of features times the variance of the encoded features. So as you can see, this is 1 divided by something. So it's going to be a small number. So it's going to be a number that is less than 1. This is going to give us very wide blobs. It's going to try to aggressively expand the edges of the radial blobs against the edges of the other ones. So we create the support vector machine here, and then we use the function fit with the training features, which we derived from the encoding, and the training labels, which we got from the encoding. So now that we have performed the fit operation, which is the training, we're going to try to predict data. We have here the testing features, and we're going to predict what their labels are going to be. I can show you what that would look like. So here we have just a list of zeros and ones. So 1 for verb, verb, TAM, 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 verb, TAM, TAM, verb, verb, and so forth. So this is the 10%, which I think is the 118 elements of the testing set. These are our predictions. We can use we can use the testing set to get our more advanced metrics, like a confusion matrix, and then accuracy, precision, and recall. So here we have the function confusion matrix, and we give it the actual labels from the testing set and the predicted labels from the testing set. And we're going to ask it to make us a confusion matrix. We're also going to ask it to give us a classification report with the actual labels from the testing set and the predicted labels from the testing set. And this is going to get us our accuracy or precision and so forth. So here we have our confusion matrix. And remember that the 0 element is a tense aspect marker, 0 is tense aspect marker, 1 is a verb, 0 is the tense aspect marker for the rows, 1 is the verb for the rows. So the computer used 118 elements from the testing set, from the entire data set, and then out of those 1,180, it chose 118, 10% for the testing set. Out of those, 41 were tense aspect markers and 77 were verbs. And again, these were chosen at random. It correctly saw 35 of the TAMs as TAMs. It incorrectly thought that 6 verbs were TAMs. As for the verbs, it correctly saw that 66 of the verbs were verbs. So 66 out of all of the verbs were verbs. And then 11 were misclassified as tense aspect marker for a total of 77. So it performed well. It could have done better. We can see here that it performed better with the verbs than with the TAM, and this is confirmed when we look at the precision, the recall, and the F1 scores. So here we have the total accuracy, 86%. The precision and the recall for tense aspect markers was 76% and 85% for an F1 of 80%. And the precision for the verbs was 92%, recall 86% for an F1 of 89%. So you can see that it learned the verbs better than it learned the tense aspect markers. All right, so we have 2 more things left to do. Here we have the function getPrediction. If you remember from our video, we are formatting our data with a list of elements like this. For example, this is Kia Orana. The first one, the element in the middle is the token. The first one is the previous token. The space is just for things to align. And then we have here the following token. But as you can see here, we need to have a list with 3 elements. The token itself, Kia, the previous token, which is nothing because it's Kia is the beginning of the sentence, and Orana, which is the token that follows Kia. We have this function, which is going to take a list formatted like this and is going to return the label, the part of speech label for the token. So let's look at the function. It gets the list and then it puts it into another list. So you have a kind of list of lists. A list that contains 1 list element, nothing Kia Orana. We have here a blank returned element. And we're going to take the list of lists and transform it using an encoder into an encoded list. So this is going to replace this element for a 0, this element for a 20, and this element for a 50, for example. This is going to transform the words into a numerically encoded list of features. Then we're going to take our features and use them to predict a label using the SVM classifier. So we have the list and we predict, and out of here is going to come a prediction, which is going to be a 0 or a 1. A 0 if it predicts that the token is a tense aspect mood, and a 1 if it predicts is a verb. We're going to take that 0 or a 1 and we're going to inverse transform it using the encoder for the labels into a human readable label. So either TAM or V. And then we're going to return that string as the return element for this function. Notice that we have a try here because maybe we could be looking for words that do not exist in the training set. If that happens, then the computer is set to return an unknown label, meaning it doesn't know what word you're talking about. And then it's going to return either a label, a human readable label, a tense aspect marker or verb, or is going to return an unknown. So this is what this function here does. And finally, we have the user input. Here we have the lines for enter a sentence and press enter. It listens to the input. It tokenizes the input so that Kia Orana is converted into a list with Kia, Orana. And then this is what I have here is just like a toy example of what you need to do. It reads if the string has 1 word, 1 token, or 2 words, 2 tokens. If it has 1 token, then it constructs the feature vector, this one, like this. It takes the token number 0, which is just the one word you wrote. It makes the preceding word nothing, and it makes the following word nothing. So this is the list of features that it's going to send to the function getPredictionFromList. And so it's going to read that list of features. It's going to return a label. For example, let's just set here features to print. Kia orana. Oh, it's because I typed 2 words. I'm sorry. I need just one. Kia. As you can see, it has the features V. I'm sorry, it has the feature Kia for the token, nothing before it, and nothing after. And as a matter of fact, it makes a mistake. It wrongly predicts that it's going to be a verb if it appears on its own. Let's see what happens with orana. That one's correct. So again, if it's just one word, the token itself, nothing before it, nothing after it, it sends that list to get prediction from the list. This one returns a human readable element, which is printed here. If you have 2 tokens, what you have is something like this. You're going to have the first, the analysis of the first one, which is the token itself, the word that follows it. So the first one, the one that comes after, the number 0, the one that comes after number 0, and then the previous word is nothing. You send it to the prediction, and you get the prediction in return. And then you do the analysis for the second one, which is the token itself, orana, the second word, the one that is before it, kia, and the one that comes after orana, which is nothing. And then you build this group of features, you get the prediction, and you send it here. Let's look at an example. Oh, did I set it to print? Yes, I did. Did I save it? There you go. I hadn't saved it. As you can see here, the first one is kia, the word that precedes it, nothing, and the word that follows it, orana. For the second word, we have the word itself, orana, the word that precedes it, kia, and the word that follows it, nothing. And here we have the predictions for the parts of speech of each word. So this is a very simple example of how you can use something like a support vector machine to predict the parts of speech from a language based on a training set. You provide a training set with a list of features, in this case contextual features, the word that comes before, the word that comes after. You convert those features into numerical elements using encoding transformations. You train a classifier using those kinds of numerical transformations, and then you can get classification labels as a result. In the next week, we are going to be looking at deep learning solutions where we're going to provide the features, but there's also some algorithms where the computer is going to try to discover the features itself from the raw data.